Okay, let's talk about closing out this section because I want to talk just a few topics at the end of the chapter. Why water is the preferred working fluid, etc. So let's jump into it. So there's other fluids that can be used in the Rankine cycle or the vapor power cycle. But water is the fluid used predominantly out there in practice, especially in big systems. Why is it such an excellent working fluid? Well, it's plentiful, it's cheap, it's not toxic, it's not going to kill your workers. They can actually drink a cup of it. It's not going to kill them. Chemically stable. It doesn't disassociate. It can take high temperatures and pressures. And it has great thermal properties. It has a very good high specific heat, meaning that the mass flow rate times the specific heat times the delta T is the energy content with the flowing liquid. High specific heats moves a lot of heat. High heat of vaporization, HFG, so that when I boil it, the steam now has a lot of energy. And good thermal conductivity for transferring the heat out and into it. So there's a lot of great thermal properties for water. It's a great fluid. Why would you want another fluid? Why do we find a discussion of the organic Rankine cycle? Organic Rankine cycle, meaning it's not using water, it's using an organic fluid, which typically has a high molar mass. What's the molar mass of water? 18. Low. Simple molecule. More complex molecules that have carbon in them, organic fluids, they have larger molecules, and they can be used also in the Rankine cycle. Why? Well, it would be because of the phase change or the boiling properties. So there's a lot that can be read about the organic Rankine cycle. Often, organic Rankine cycles try to make use of low temperature heat sources. So some sort of solar or geothermal or industrial waste or just burning or biofuels or biomass type of heat source that is typically doesn't have such a high temperature. Maybe your geothermal water is 165 degrees F. This is just an example. You'd put it through an evaporator, a heat exchanger, to transfer heat into the working fluid. This is acting as the steam generator or boiler. Then you pass it through the turbine. The turbine drives the generator to make electricity. And then you put it through the condenser, typically dropping it to the atmosphere, to a lake, to the ocean, to the river, and then pump and away you go. So this is the traditional Rankine cycle with a different fluid. We could take a look at different fluids. This is plotted using some software that I'll describe later, but you can get it. It's RefProp, and I have some videos about RefProp out there. It's put out by the NIST, National Institute Standards and Technology, basically a government organization. And you can plot for property R22, the fluid R22, the temperature, entropy diagram, the TS diagram. And then you can see the dome. What's this up here? The CP, the critical point. And saturated vapor, saturated liquid. And then you have lines of constant pressure, 1 MPa, 3 MPa, 5 MPa, out to 9 MPa. Just throw a few out there. And we want to reject heat out of this cycle. Think about putting on here the Rankine cycle at around 300 Kelvin. But we don't know exactly what is our heat source. Maybe we can burn a fuel that comes in at 400 Kelvin, maybe 450, but it's typically not as high as we'd like. We have a low temperature heat source. So if you were coming in at 400, right, and that's going to be what's coming out of the boiler or out of the steam generator, evaporator. That's what goes into the turbine. What happens? You're going to, let's say you were way out here, 1 megapascal, 400 Kelvin. Whoops, I guess I'm up here. And then we're right there. Drop it, reversible expansion. That would be the best you could do through the turbine, right? Well, you don't want to be out here before you have to reject heat in the condenser. So So think about the optimal is somewhere at 300 Kelvin. Saturated vapor is what's coming out of the turbine. Somewhere right in this vicinity is what's coming out of the turbine. Got it? Going into the condenser. So now, what would you want if you were going to use this fluid, and that was your high temperature source? Your sink is fixed at 300. Well, somewhere there. You know, I'm going to probably have to run it around 5 MPa. See how we're doing that for design considerations? Kind of picking that fluid, looking at our pressures, making it fit for the Rankine cycle. Here's some property values for that same fluid, the different software but different feature of it. So I said, okay, 300 Kelvin, let's put it quality of 1. Those two pieces of information allowed it to give me the pressure, the density, the enthalpy, and the entropy, okay? And then I said, on a TS diagram, same S, but now 400 Kelvin, the same S, same entropy. See what I did? And now I can see, oh, I'm going to have that boiler at 5 megapascal, 5.3 megapascal. It sort of tells me what pressures I'm going to be at. And see how things fit in the system. What happens if I would be able to bring it up to 450? Well, then if I really wanted it to end here, I would be really high pressure. It would be a supercritical Rankine cycle. As it went through the boiler, it wouldn't undergo a distinct phase change. Actually, for this case, it would be kind of the limit. This would be like supercritical as well. If you were able to have it here, then it would go through the boiler and have a distinct phase change. It would be a traditional Rankine cycle instead of a supercritical Rankine cycle. Let's take a look at another fluid that's used. This is R11. Look at the shape. You see the difference in the shape of the TS diagram of the dome? What's unique about that shape? It's critical point. Look at this. In this region right here, what do you think? Straight up and down. Straight up and down. And then here is the saturated liquid. Let's say we have 300 Kelvin. Let's say we think we want to bring it out right there. What about if I have 400 Kelvin heat source? I could have it right here, and I could pass almost saturated vapor into the turbine and come out with saturated vapor at the exit of the turbine. It would have to have a pressure somewhere between 1 and 3. I think I ran the calculation. It shows 1.3 megapascal pressure right there. Okay. Notice also when back in here I said describe this state to me for the quality. What did the software cough up? It said undefined. True? Let's go look at this. It said for this state right in here, what is the quality? Oh, it's slightly superheated. Slightly superheated. Right? Why is the other one undefined? Because it's basically above the critical point temperature, and so it's supercritical. It's somewhere nebulous out there, supercritical region, okay? Now let's continue on to another fluid, the third and last fluid that I talk about today. There's plenty of potential organic Rankine cycle fluids. But isopentane, look at the shape of that TS diagram. What do you notice? So if you go from the critical point, you come down, what about the slope on this line? Before, it was sloped like this, then it was like this, and now it's sloped like this, isn't it? So let's just do the same game. 300 Kelvin, I'm going to reject heat to. I'd like to bring it into the condenser as saturated vapor, or out of the turbine as saturated vapor, right here, right? So if I have reversible expansion through that turbine, and my heat source is 400, where is the inlet to the turbine going to be? And what do you see? You see that that looks like it's two-phase. Yeah, it is. It's around 68%, 69% quality. That makes no sense. You're not going to feed the turbine two-phase, but theoretically, looks great. What are you really going to do is you're going to bring this over and stop, and it's going to be saturated vapor coming out of that boiler. You're going to feed that into the turbine, and when you do, what's the condition of the fluid on the outlet? It's now superheated vapor at low pressure. So when it goes into the condenser, the first little bit of heat removal does what? It does de-superheating, if you like that term. It's cooling down the vapor before it starts condensing in the condenser. This is what they call dry organic Rankine fluid or cycle. And this one back here would be wet because you're more common to have water droplets at the outlet of the turbine. And then this one, not dry, not wet, they actually call it something like isentropic. Isentropic because it's straight up and down on that edge. Let us talk about solar concentrating power to feed into a Rankine cycle. So these things have been out and talked about since the 60s and the 70s. They built fields where they've had mirrors, and they focus those mirrors or heliostats so that the sunlight gets focused on one little receiver. And just think if you had a football field or 2 football fields of these out there, you could focus a lot of energy up there. The sunlight would be very intense, right? And that's why, and the temperatures can be very, very, very high. Here they don't show it, but let me modify a little bit. You could take an oil or liquid metal and run in a loop down to a drum and then back up again. Why? Because you can really change the temperature of a liquid metal or an oil or something without boiling it. And if you boil it up there, then it's a lot larger volume, and now you've got to have big pipes to bring the vapor down, where it's just small pipes to bring oil or liquid metal up and then liquid metal down again. And then you bring it down, and this goes in a loop, and it'll get spanking hot down here. It'll transfer its heat in a steam drum or a steam generator to water that comes this way. Now you bring out steam out of this steam drum, pass it through this turbine that drives the generator, electric generator, to make electricity and sell electricity. Out of the turbine, you have some high quality steam or slightly superheated vapor, and you bring it over to a condenser. This condenser is shown that it's air-cooled condenser. Put it through a pump and then back again. So this is the Rankine cycle. This has been kicked around for a while. It's just difficult or expensive to build and then maintain. I don't know where there's an existing facility. Maybe there's one in California, but they work great in the desert climates. What's the other solar to make electricity? Photovoltaics. What's that? Direct sunlight hits electrons, pops them off, and then boop, you got electricity right away. You don't put the energy into any water, no phase change or anything. Photovoltaics, PV, right? CPS Energy's big on PV. CPS Energy's unfortunately not interested in solar concentrating source for generating electricity. So you can integrate solar storage of thermal energy, because when the sun goes down, a lot of times you still like to make electricity. So here's a design, I'll just show it to you. So you have troughs and you have oil that goes in a circuit, and it then goes through a heat exchanger where it boils the water. So the water is boiled in the boiler, steam boiler. Then the oil is cooled and it goes back through the solar trough field. Okay. Once the water is boiled, then it goes to the steam turbine, then the condenser, pump, and that's our traditional cycle. You have to reject heat somewhere. Where are they showing you to reject it to and how? This is a large concrete multi-storied cooling tower. And one of the reasons it works so well is it intakes water near the bottom, air, surrounding dry air from the bottom, or even moist air, whatever air, outdoor air it is. And you have water spraying in here, and then you'll get a natural chimney effect. You don't have to have a fan. It'll naturally, hot air rises, cold air sinks. the chimney will come up. Also, what helps is the molar mass of water vapor. What's the molar mass of water? 18. What's the molar mass of dry air? Around 30, 29, 30. So even water vapor is light, cloud, it goes up in the air. So it'll have a great chimney effect. You don't have to have a fan or a pump to move the air. Okay, now let's take a look at storing the thermal energy. When the sun is really hot, maybe it's making so much hot oil, you can divert some of the hot oil down to another heat exchanger where the oil is going to be cooled, and hot salt or cold salt coming out of here becomes hot on this top side. So the salt, maybe it started with a full tank of cold salt, and as you want, you transfer the salt to an upper tank, and it fills up that upper tank as the level in the lower tank goes down, and now you have a tank full of hot salt. As a design engineer, you size it and that to make it work for the overcapacity of the thermal intensity in the hot part of the day with the sun's out. Then when the sun starts to wane, these valves change, and you can then you can shut off the flow of oil to the solar trough because maybe the sun is now set, and the pump could run the oil backwards through the same heat exchanger. This time the oil isn't giving up heat, it's absorbing the heat, and the salt runs backwards and recharges or flows into the lower tank, which is your cooler tank. And so it's transferring heat out of the salt into the oil, comes up and drives the boiler to make electricity. So what you can do is you could see that as a day, in the morning, noon, evening, midnight, the sun is up, it's coming up, you're starting to make electricity. You get up to about 100% capacity for the steam cycle. This rest of the energy you push off to storage, thermal storage, and then when the sun starts to come down later in the day, instead of it just all going to zero, this is when the sun is set, you take some of that energy out of the thermal storage to continue to generate electricity. So those are the concepts that are out there. Cogeneration. It's a concept that you'll hear kicked around. It means making power as well as doing something useful with some low-grade heat. Maybe you burn some expensive fuel, you make some electricity, but then you also make some steam that goes out to the middle of Chicago in the middle of winter, middle of New York in the middle of winter, and heats up big buildings. And they'll have those centralized plants that provide heating to buildings in the middle of winter as well as electricity. And so this was a homework problem, right? The only thing was you had to renumber the system because this illustration wouldn't allow you to do it. So hopefully you realize that this coming out at 6, you had to know what comes out. That's not the same as what came out here, let's say at 2, because it heat transfer to the steam in the district heating concept. This is the process load. And then this state 5 should be moved over, and 6, they come 5 and 6 mixed to create state 7, which is fed into the pump, which you might as well renumber to 8. The idea of cogeneration is make power plus do something else that's useful, some other manufacturing process or heating need. Carbon capture and storage. There's more and more concern, and over your lifetime, there'll be even more concern about CO2 emission, true? And what's effect on the atmosphere. So they don't want as much CO2 emitted in the atmosphere. If you burn something, you burn natural gas, you burn coal, oil, that's where it goes. It goes to CO2. It goes to water vapor. The hydrocarbon goes to water vapor as well as carbon dioxide. So one of the ideas is to go ahead and burn the CO2 producing hydrocarbon fuel or carbon fuel, but extract the CO2 from the emission, and once you extract it, do something else that may be productive and useful with it. So this is the carbon capture out of, and maybe you store it, or maybe you put it somewhere, or maybe you use it in some way. Well, there's some discussion of clean coal, and embedded in that idea of clean coal is you're going to have a more complex use of it, burning it, such that you don't put things like mercury and sulfur up the stack with the emission. Going to clean that up. Plus carbon dioxide, clean that up out of the emission. So these have been kicked around for at least the last 10, 15, maybe even 20 years. So an integrated gasification combined cycle. So they take the coal, they gasify it so that now it's like burning a fuel that's like a gas, like a natural gas. They call it syngas, synthetic gas. So integrated gasification combined cycle. It removes the impurities from the syngas before it's combusted. Sulfur, and you can do good things with sulfur as well as the mercury. Those are the two bad ones. It's interesting, though, that this is a great Wikipedia site. We're going to take a look at an illustration. It won't be this one as to how it works. But down below, near the end of this, it talks about, right here, the emissions controversy. Senator Harry Reid, anybody recognize that name? U.S. Senate, most powerful man in the U.S. Senate, right? Majority leader from the state of Nevada. In 2007, in the Clean Energy Summit, said he will do everything he can to stop construction of proposed new IGCC coal-fired electric power plants in Nevada. Reid wants Nevada utility companies to invest in solar energy, wind energy, and geothermal energy instead of coal technology. Reid stated that the global warming is a reality, and just one proposed coal-fired plant would contribute to it by burning 7 million tons of coal a year. The long-term health care costs would be far too high, he claimed, no source attributed, but, quote, I'm going to do everything I can to stop these plants. There is no clean coal technology. There is cleaner coal technology, but there is no clean coal technology. Okay, I thought that was very interesting. You're going to find that when you get out there and practice, politicians can turn policy on a dime, and you can be in a job and out of a job, in a career and out of a career. You can be, it doesn't take much. When the president was elected, he killed the high-level waste repository by turning off the spigot of federal funds to it. That fast. Oh, no, he didn't say he killed it. He just, no funds for it. That's how you kill things in Washington. You defund it. It's exactly what happened. Anyway, this, you will find more of that. One of the things about this thing that I'll just point out is there's a boom in sale of coal in the United States. But the coal consumption to make electricity in the United States is down. But we're selling a lot of coal, we're mining a lot of coal in the United States, but we're not burning a lot of coal in the United States in 2013, 2014 to make electricity? What's up? It's all going to the coast, getting on big ships and going overseas. And they're soaking it up. And what do they do with it overseas? They burn it. Now, does the air you breathe ever pass over India, China, South America, or any other country, or does the air in Nevada stay over Nevada? So guess what? It takes probably less than 24 hours for that coal emission in some foreign country to pass over. It's not a little isolated thing. So great that Nevada's going to have clean air, but as an engineer, you've got to think through these things, really. Because you look at this statement, it's like, so sell it overseas. That's great. You know, there needs to be more engineers in the Senate. I completely agree. What you do is get an engineering degree, then get a law degree so you know how to argue, and then go to Congress. Please, I'm begging you. I'm begging you. Yeah, engineer that knows how to argue. All right, let me move on. So let's take a quick look at this. It's when you have a complicated diagram like this, find your ins and find your outs, right? Where are my ins? Guess what one N is? Coal N. Okay, where's my other N? You have to look a long time. There's an air N. And there's an air N. Is there any other N's that you see? Any other N's? I got 2 airs and a coal. They better put some water in this system anyway, because where is the water coming in? Rain. It's somewhere. Anyway, there's another N. It's not a perfect diagram, okay? There's got to be some water. Let's find some of the outs. What's this out? Slag. And so it's some junk that's not the carbon, not the stuff that'll volatilize when you burn it. Okay, where's another out? We got a steam out right here. Actually, okay, that's fine if it's a steam out. Okay, where else? There, sulfuric acid, then there may be a useful byproduct. You got the sulfur out, so it's not going up the stack. Anybody, y'all know we did a great job of cleaning sulfur out of the coal-fired power plant emissions. That was done in the 60s and 70s. But there was a thing called acid rain. Historically, you might want to look at it. And it killed a lot of things. And people said, what's happening? And especially up where you had shallow soils in the Northeast, you had granite, and then you had shallow soils. A little bit of acid rain turned the soil to a high enough acidity then it kills the wildlife. Not the wildlife, like animals, but plants that were sensitive to the change. We're heavily alkaline down here. We could probably use a little bit of acid. But anyway. So also, what else is an out? Urea. What's that? White powdery stuff. It's fertilizers. Farmers want to buy it and spread it on their fields. Okay? CO2 is an out. Hey, we concentrate it, we can sell it, put it in a pipeline, or do something useful to it. Electricity is an out. Power is an out. There is some emission stack. Let's take a look, though, what happens. So you have something where you're adding oxygen and air. They get rid of the nitrogen out of the air, and they push it over. That'll help you make your urea. But you try to make syngas. So you have a gasifier that makes syngas. You put in the coal, oxygen, and you make some syngas. You remove then the particles, and I'm not certain about shift reactor. Mercury removal, you want to get that out. And then you clean it up, get the sulfur, and then you could take the hydrogen-rich part, make urea, carbon dioxide, try to get that out, but you're going to bring it down, the syngas, and you're going to put it through a gas turbine, burn it like natural gas to make electricity. Now, the gas turbine takes air through the compressor with that fuel, then goes through the turbine, but it's still high temperature. So you put into a heat recovery unit or steam generator. There has to be water supply to this. To make some steam, you could pass it through a steam turbine to make more electricity. And then you've got to add some because you're going to take steam and needs to be brought over here to the gasifier to make syngas. You need steam, you need oxygen, you need coal to make it. So I give you a taste of it, but this is productive. You could sell it. The CO2, find something useful. Don't put it in a smokestack and make electricity with a gas turbine as well as a steam turbine. You know what? They had this proposed in the state of Texas. You can read about the Clean Energy Project. There's a whole website on it. And they're using the integrated gasification combined cycle design. That's it. Guess where it's going to be built? Right here is called Penwell, Texas. Here is San Antonio, Fort Worth, I-20, I-10, El Paso, Mexico, etc., right? So way out there, that's where they propose. These things take a long time. As they propose things and they start roll, it doesn't like you can build it overnight. Why were they going to build it out here? Because they could do something with the CO2 that would be useful. What were they going to do? They're going to inject it down below, sequestration, down below to stimulate oil production in the Odessa Permian Basin, right? That was before the big happy smiley face came online down here. What's this? Shale, Eagle Ford Shale. And before another big blob about 5 times bigger over here, the West Texas Shale with fracking, right? This one's billions and billions. Did I say billion? A lot of money. This one's 5, 10 times a lot of money. All right, a lot of careers too. So that kind of changes the dynamics a lot, because how hard is it to get a worker to work out there in that rough environment anyway? And then how hard is it for them to work on a power plant at nominal, even union wages compared to the boom oil field wages? Very difficult. Plus, natural gas was high. Natural gas has plummeted. Price of natural gas makes it like, why would I want to do this anymore, right? And so CPS Energy, hey, do they have a service area? Does CPS sell electricity out in this region? No, the service area is right there. That's it. Bexar County and very little about, not all of Bexar County, most of Bexar County and just a little bit of Comal, Guadalupe, Medina, etc. Okay, it's like Bexar County, City of San Antonio, CPS Energy. But they invest in this clean coal plant way out in West Texas. I've been talking about this every time I teach Thermo 2. And so in 2012, there's a news announcement that we committed to buy 200 megawatts of the electricity, and it's a 400 megawatt plant. That's half of the output. Now the plant costs a lot of money to build at that time, $2.4 billion. But it's going to have that carbon capture, storage, coal gasification, blah, 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 urea production, good to farming in the panhandle. They were going to get $450 million from the U.S. Department of Energy's Clean Coal Power Initiative. They were going to get 211. They may have already gotten all this money and then spent it. I don't know. But in 2009, American Recovery Reinvestment Act, the stimulus, $211 million of future debt given for this project. Anyway, they even got clearance from the TCEQ, and a lot of things were looking good, but the dynamics were changing. And what happened just this year, January of 2014, CPS Energy, who had an agreement, decided to let the agreement expire. It did expire. Basically, they pulled the plug. So they had a 25-year purchase power agreement way back 2011. They were all excited. It's going to be first of a kind, clean coal power plant, captures 90% of the carbon dioxide, enhanced oil recovery, West Texas. No more. Done. So there you go. Hopefully you enjoyed that.